Let me restart today. Okay. Reconsidering some the last exercises with the M file, in which I don't know if you remember, I tried to optimize both. What is the meaning of both? N order of the polynomial. We will see that I already told you last time that N reflect the number of coefficients. Starting from now, I will speak about number of coefficients, because after this repetition, I will consider another regressors, the trigonometric regressors. Of course, we can consider many regressors, no, exponential regressor, wavelet regressor. We can mix regressors. To choose the best family or the best combination is a non-convex optimization problem, because we have to choose, we have to minimize with respect to the number of coefficients, and in the meantime, with the coefficient itself. Do you remember this minimax problem, or better to say min-min? The idea is to minimize both error, deterministic error and stochastic one. Probably it makes sense a little bit to flesh out again the last two slides. In order to yeah. Yeah, just to recall the problem. Probably this one. Zoom isn't a problem in chat. Ah. Excuse me, I lost Zoom now, blocked Zoom. I have to go out again. Yes, the problem with Zoom really totally blocked. Okay. Let me. Yeah. This is the problem to offer the hybrid lecture. For me, should be easy to do the lectures in the presence, because this kind of problem with Zoom, no chance to work with Zoom now. Okay, let me see if I close some. Let me see. Okay. Finally, you remember this idea? We described the process, the reality, let me say, considering two kinds of errors, statistical and deterministic one. Then you remember very quickly this possible solution. I don't want to go in depth. I didn't explain much about that. But think about at this point as y over line, the mean value. And then we can see that this triangular structure, which we have here 90 degrees, we can see that this difference here between y and y hat represent our SSE. This vector here, y hat minus y over line, represent SSR. And this vector here represent SST. Therefore, do you remember this possible structure in which we have, thus the data, roughly speaking, can be split in two forms of errors. Do you remember I told you the reality is in the form of errors? This philosophical sentence. The reality, the measurements, is in the form of error because of two errors in our concept, because can be seen using this model here, which came very quickly. I didn't explain the calculations from this approach of the form of error. The idea is to minimize both. In this sense, deterministic stochastic one. Now, in order to do that, I don't have time to repeat everything. We need a cost function which must be convex with respect to theta and with respect to n. Or better to say, do you remember I told you, if I use just r squared, this cost function here, and now I will show you again with the example in MATLAB, r squared can be used to minimize SSE, to minimize the deterministic error, but cannot be used to minimize n. I mean, I cannot choose the best n. Of course, the idea is to choose the compromise between both. I cannot minimize both totally. Do you remember this stupid but interesting example, didactically very strong, in which we can see already from this example that in this case here, the deterministic approach, we minimize the deterministic error, r squared equal 1, but we maximize the stochastic one. We can see directly, let me say from here, because SSE is 0, r squared is 1 in this case, and SSR is equal to SST, the maximal one. R squared change between 0 and 1. Now, in order to find quickly, or to try to find a convex function with respect to n, because here, again, I am analyzing, I am testing n, r equal, r squared equal 1 means n equal 1. If I consider n equals 0, we have r squared 0. This means the minimal statistical error, but the maximal, we have seen last time, deterministic one. Now, modifying in this form here, we hope that we have a convexity with respect to n. Why that? Because p is n plus 1. Now, starting from now, we will speak about p, the number of coefficients. Because through the number of coefficients, we can compare different families. Because the idea is to find a family, regressor, let me say in general, a regressor, because the regressor can be also in a combination of different families. I can combine polynomial and exponential function. No? This is possible. Of course, the problem becomes not convex. Here, increasing n, as I told you, I didn't demonstrate, but SSE, nevertheless, we have seen here. SSE we will reduce. When I meet all point, it will be 0. But also the denominator here will tend to 0. M is larger than P, much larger than P. Increasing P, because I am increasing N in this case, I will reduce also this one. This means it's not clear. It could happen that they have an optimal, also for N. Question is always, but it seems to be something arbitrarily, no? Because why this modification? It is. basically the choice of the cost function is one of the big problems in optimization. It's the big problem because this is really something which is depends of our sensitivity, how we image, how we can figure out our optimization problem. This is really something, therefore, we have many, let me say, cost functions. We will see also, I don't know, in the next lectures, but if you consider some books in optimization, we will see that there are extremely many metrics. Metrics means a cost function. Probably students who is attending class in data science, you know, many cost functions, different aspects to emphasize different aspects of the phenomenon or the phenomena which we want to analyze. Min. Remember, this I told you. The idea is to find the minimum of the deterministic error, SSE, with respect to theta, in this form here, and the minimum of everything with respect to n. Typically is a non-convex problem. Now we will try to show you again how we can find, thanks this trick, this correction of R squared, the convexity in a particular problem. And then I will switch on the trigonometry function. Okay, let me open again as last time MATLAB. This was a little bit in a repetition in order to look. If you consider, for instance, in my study, you have starting from polynomial zero. Look here. We have here the exploration data X in column form and the measurement Y. Let me consider the trivial example in which I would like approximate the data using a polynomial order zero. Last time probably I didn't show you, but I can do that. Of course, this will typically this we don't consider this. Why that? Because it's not a compromise. Please pay attention. Optimization is always a compromise. It's not a compromise because you remember this case here minimizes, or that this approach, just to calculate the mean value, the constant theta zero, minimizes the statistic error, but maximizes the deterministic one. In this sense, we will see that is the minimum, the absolute minimum of R square adjusted. We will see it's zero. But it's not our goal. Our goal is the relative minimum. It's not the absolute minimum. In a local minimum, in a compromise. At least it's not exactly correct what I told you now, but we cannot consider an extreme situation in which I minimize the stochastic, but I maximize the deterministic. We have to find a compromise in between, because the optimum in our case is the minimum of deterministic and the minimum of the stochastic. This is the goal. Even though it could happen that is not the global, I would like to understand, you will understand better when I write the data. Look here. Do you remember why now the exploration matrix is just in a column with 6 ones? Easy, because if you have a 6 point, this is an example. Once, because you remember the last row of the exploration matrix is 1. It's corresponding to the polynomial order 0. Should I come back to the lecture? Or is clear? It's clear. This is fixed. When you use the polynomial order 0, you have just in a column of 1. Basically, what is the polynomial order 0? It's the mean value. Y over line is to calculate the mean value. Here I change just the variable because I don't want to change anything in the rest. This does not change anything. Do you remember last time I clarified that we have R squared? Here we can put here, instead of this long expression, relative long expression, this in this case is not long, but when we consider polynomial, higher order will be longer. You can write directly ys. It's clear. But I put for the student in order to be more clear. And putting m equals 6, n equals 0, just to know, p n plus 1, I can modify exactly r squared, just copying r squared and putting this element before SSE divided, I multiply this element with SSE divided SST, and I have my r squared adjusted. It's clear this once, né? Because it's polynomial order 0. Let me run. We can see 0, as I told you. 0. 0 r squared, 0 squared adjusted. We don't typically we don't consider absolutely this solution because it's a solution that doesn't minimize both, minimize just the statistical error. As the example which I introduced at the beginning. It's clear that this theta 0 is the mean value. We can also calculate it, but this is the mean value of what? Excuse me. It's the mean value. It's the mean value which came from the analytical solution, which is this one, in case polynomial 0. Let me consider the polynomial 1. In the meantime, I try to build, and then I will share. I try to write for you what happens. No? Okay, let me consider now, and then I will show you the graph. Let me consider now the polynomial order 1. For the same example, we can see that the data, believe me, are exactly the same. If you don't believe me, I can show you. This was before, this is exactly now, huh? Exactly the same. It's clear. What I am doing now, I trying to proceed with trial and error method to find the minimum of SSE and SSR with respect to theta. We see theta 0 at this moment. With respect to n is equal to 0. Look, polynomial order 1. Here we have as a comment the structure of the polynomial. This is the structure of the exploration matrix. Here I don't change anything. Let me run. Look at the value now. We have here R squared adjusted. R squared is 0,9819. Let me copy the value. So later we can understand a little bit what I am doing. And R squared adjusted is 0,9773. Graphically, we have this solution here. But again, graphically doesn't mean anything, just to figure out. Very important for us is the values, because in a quantitative analysis of our approach, our method, is from the picture we cannot say anything. It's good, the bad. Now we will see. Proceeding ahead with what? With n equal to. And then we will compare R squared in order to show you again that R squared is not a suitable parameter, or cost function, better to say, indicator, no? Because we will see that with respect to n, please pay attention, with respect to n is a convex function. is not convex function, it's monotonic function. This means we cannot use, as I told you many times, R squared to optimize with respect to the number of parameters. This means it's not useful for us to optimize, to choose between polynomial and trigonometric or whatever other kind of families or combination of family between regressors in general. Let me now open the polynomial order 2. Share. Polynomial order 2 is already open here. You can see here from the comment. Not only from the comment, but also from the exploration matrix. I don't know, I insisted a lot in the past lecture. The rest does not change anything. Let me run. R square is 0.9842. Zero comma 9.842 and R square adjusted 0.9736. Second, 0.9736. To figure out what happens is this one. Now, is better or not? It's better with respect to n equal 1. Why that? Because R square adjusted is less, in this case, than before. The idea is to find if exists minimum. It seems to be from the value, from optically we cannot say. Let me go ahead. I mean, let me show basically more practically what I intend. You can see that between this we didn't consider, this we didn't consider because it's not a compromise. We can see that R square adjusted is increasing, excuse me, R square is increasing, but here is decreasing. This R square adjusted represent a min-min. You remember in the theory, represent a min-min. This is our goal, to minimize this. Of course, we will see now what happens. And then we will be able to choose. But in any case, now we can see at this moment that the case, this case here, n equal 2, this is n, I analyze in n, is better than n equal 1. The risk here, that is going to 0. If I go into 0, I cannot accept. Why that? Because the function is monotonic one. I will end up again in an extreme case in which n equal the R square adjusted equals 0 is the minimum for stochastic, but not for deterministic. This I hope that somewhen is for some n, we will increase. This means we found a region of n in which we have the convexity. And we assume that the first n which we find is the best one. I clarify a little bit better later because it could happen that increasing, I will find something better. But why we assume that the first one is the best? Because a goal in at least in engineering field, when we hope we use this method online, is also to use the minimal number of parameters. This means typically we stop at the first convex region. But of course, Nobody knows, no God knows when, for which n we have the global minimum. But in any case, it's not acceptable 0 for the same reason as before. First of all, the concept that we cannot accept a function which is monotonic, no? Because does not represent any compromise. But in general, if 0, we have the minimal value of the stochastic error, but the maximum for the deterministic. Let me now try with t, with n, equal 3. Let me show if it's here. No, I have to open from here. Yeah, we can see that the value are exactly the same. The polynomial is here. Here is the exploration matrix. The rest of the program does not change. Here, please pay attention. You can, instead of write this long expression I told you as before, exactly the explicit form of the polynomial, you can write ys. Because this expression is exactly our polynomial. This is SST. The sum of y measurement minus the regressor y hat is the SSE, excuse me, SSE. Also in R squared. You can write directly ys, because we can see it's the same, but I put for you just to be more explicit. Let me run. You have seen also last times. Now, we have R squared still increasing 0, 9, 8, 5, 3. 0, 9, 8, excuse me. 0, 9, excuse me, 9, 8, 5, 3. And their square adjusted 0, 9, 6, 3, 1. This means it's decreasing. 0, 9, 6, 3, 1. The situation is this one. Here is still decreasing, and here is still increasing. Now, let me show you how it looks like. This is the solution, graphically. We still minimizing SSE because R squared is increasing. Do you remember? R squared is increasing, we minimize SSE. And we minimize also R squared adjusted, which basically is the minimum of both. We can see directly in R squared adjusted because we are decreasing R squared adjusted. Let me conclude now with the last test, polynomial order 4. The example is the same. Let me run directly. Does not change anything except for the exploration matrix and the regressor. No? Let me run. Look now what happens. The R square is still increasing. And now the R square adjusted is increasing. This means the polynomial order 3 is the best one. Let me put the value and then we'll discuss. R square is 0,9944. Still increase. R square adjusted 0,9720. Look, so we can figure out better. Yeah, we have we increase. This means we reduce SSE. Then we have something like that, which here we have the best value, the minimum, with respect to n. And of course, in the sense of the compromise in between, is what we are looking for. No? Because here's the situation which is in a compromise between, as I told you, the error in SS stochastical and deterministic error. This is in a compromise. Let me see between both. Let me see if I forgot to say something. Also because we have the a limited number of coefficients. No, the coefficient is 4. But of course, it could happen that it depends of the data of the phenomenon that we have for larger and larger n and a better minimum than this one. But typically we stop at the first one because of the limitation of the coefficient which we have. Let me think if I forgot to say something. Probably I can comment why we don't consider this. Yeah, first of all, with respect to n, the situation here, n equal 4, we can see that r square adjusted is not, this is the best in term of r square adjusted. But also, if you think here, it's true that we minimize SSE here much more than this one. But typically, the goal is to minimize R square adjusted, because if we minimize just R squared, remember, we end up in an overfitting, because R squared does not consider, in the sense, the stochastic error. Because minimizing R squared, we assume that the data are free from errors. But in general, we cannot accept to minimize as a function which is monotonic in the sense. No? This is our compromise. Okay. Now, let me upload another presentation, and we will start with very shortly, nevertheless, presenting the trigonometric function or regressor. Let me. No, yeah, the lecture looks like something like that. You can find in my study. Just a few words about the theory of the structure, and then we will see together with MATLAB. As I told you, the regressor can be whatever kind of functions or family of functions, or combination of different families. Yeah? I can combine sine cosine with exponential, sine cosine with exponential and polynomial. Of course, in this case, the problem is most of the time not convex. Yeah? This means we have to look for a minimum in a particular way. Now, at this moment, the example which I presented before was in a trial and error. We will see that with the PSO, starting from next week, it's in a structured method which can find in any case a possible optimal solution. Of course, we are not sure about the global solution. There's no methods guarantees the global solution for a given cost function. This means in general the global solution for a real process is impossible to be found because it depends of the cost function, which could be different depending of the sensitivity of the designer, no? Of the people who is analyzing this problem, but also to find for a given cost function, to find the global minimum or optimal is impossible. We cannot be sure that we find the optimal solution. Trigonometric function, you remember, is also known as a Fourier function or Fourier basis. No, I didn't distinguish here between function basis because it's a more mathematical aspect. This question here, basically, we already introduced, how to choose appropriate functions, exactly what I told you until now. Basically, when we have more than two possible regressors, you will find the regressor which minimize R square adjusted with the minimal number of coefficients. In this sense, you can choose between trigonometric and polynomial, or also mixed regressor. I mean, if the criterion is to minimize, for instance, one possible criterion, a const function, and in particular, the R square adjusted, you will try to find the minimal R square adjusted, as we did before, for comparing what you have for trigonometry, for instance, and the Taylor. This means the function or the family which have the minimum R square adjusted and the minimum number of coefficient is the best one. But of course, it could happen that we have the minimum R square adjusted for the trigonometric, but obtained with a larger number of coefficients. This is a little bit difficult, the choice. I don't know if I try to, if you want, I can come back. Assuming this is what we obtain exactly now for the polynomial. Now, if I do the same exercise for a trigonometric family, I will obtain a better minimum, but let me say for n equal 5. Now the question is, what is the best family? I have R square adjusted that indicates polynomial, but the minimum is obtained. Excuse me. The R square adjusted is better for a trigonometric if the trigonometric is better, assuming that the trigonometric is something like that. But the trigonometry is obtained with a maximal number, with a larger number of coefficients. Now, yeah, it depends how many coefficients. Of course, if the coefficient is not so much, we will, it's not so many, the difference is not so much, we can consider directly the better R square adjusted. But of course, if I have to implement a regressor with, as before, with much more and a lot of coefficients, yeah, we prefer to sacrifice the R square adjusted value and to implement a regressor with a less number of coefficients. But in any case, R square adjusted allows to choose which one could be considered. Of course, the easy choice is smallest R square adjusted and the smallest number of coefficients. It could happen that these two elements don't match. But now we have nevertheless a criterion. Of course, if we have a mismatch, we have to be sensible. If I increase just one parameter, yeah, it depends then what is the difference between the R-square adjusted value of the polynomial and the R-square adjusted value of the regressor. For one coefficient, it could be that we can evaluate a little bit the choice, but one coefficient is not a big difference. Depends R-square adjusted value in the sense. Yeah, trigonometric function is totally different with respect to polynomial. Think about the proposition of Fourier, which says each periodical function can be approximated through a summation, or the summations in general, of sine and cosine functions. This is the idea. This means the idea is always to approximate function, but here it seems that the hypothesis is periodical. Not necessarily in our case, we have a periodical measurements, or the phenomenon, it could happen. In the nature, we have many periodical phenomena, but not all phenomena are periodical. This means it is possible to apply, it is. But of course, we will find also in this case a possible compromise. Let me go ahead. I don't want to be boring with the last part of the lecture. Probably you know, if you are an engineer, if you don't know, it does not matter. Very important here to look at the difference, because for us, very important the structure of the regressor. We have seen until now the polynomial basis or function of the regressor. Forget the word basis, even though makes sense. Because when we mix, for instance, trigonometry and polynomial, we don't speak about basis. But this is mathematical aspects, and forget this. For us, it's a regressor. We have this regressor here. Let me compare. This is two possible definitions. No? We have a constant part, A0 divided 2, AN. Do you remember this represents the mean value? Do you remember we have seen? Or the crossing depends, no? Depends. This depends of n is the mean value. If you have a polynomial or the zero, otherwise is the crossing parameter if x is equal to 0. But this is also mathematical details. Don't care about that. This is the structure. This is the structure. You have a constant here. You have a constant here. Quite similar. Divided 2 is there just historically. You can throw away if you don't like. It's a constant. You can rename A0 tilde this constant here. Anyway, we have two constants. Then we can see that we have elements, which depends in this case of k, we can see here, instead of n. Here we can write again everything in terms of equals sum I from I starting from 0 up to n, I multiply x up to I. No? Anyway, you know that the polynomial can be written also in a summation. It is in a summation, which now the index is a general index I from 0 to n. Probably you know, no, we can write this. This means the summation is no problems. Or if you want to use the same notation instead of I, k, no? K from 0 up to n of a k x up to k, the sum. Exactly this expression here. Here we have this similar sum, but look, here we don't have exponential element. We have a k. We basically it's something related. What is here k? K, if x represent as x represent the exploration variable, no? X represent this exploration variable. K, the dimension of k in this case is t divided x. In any case, using x, I can calculate my value as before. I don't know if you remember this y hat x1, y hat x2. The concept is basically the same. Starting from k equal 1, because k equals 0 now is included here. No? K equals 0 is here. We can use this element here as we did before. Let me show you here. Let me skip everything. We don't have time. Look here. Exactly what I told you now. You remember this? I told a lot about this. I told a lot, this structure here. Now, what we have here is exactly the same, exactly what I tried to explain now. Because, as I told you, I can find y1 hat considering x1 in the regressor here. I can calculate y2 hat considering x2 in this regressor here. And I can build the matrix as I did for the polynomial case. I don't know if it's clear. And of course, I can separate in this form here, in which, of course, here, and it's given the number, the maximal number of coefficients. It says, yeah, the coefficient is if the coefficient here is p in the Taylor approach, here in the coefficient is 2 times p plus 1, 2 times p plus 1, because we have a sinus cosine. This does not mean that necessarily is more than here. It depends on the value. Yeah, the coefficients, if the coefficient is p, here generally the coefficient 2p plus 1, but this does not mean that we have more coefficient in trigonometry with respect to Taylor. This depends on the value. Let me show you more in detail where this matrix comes from. I have a slide, but I think it's intuitively clear. But let me show you more mathematically. Yeah, I have an interesting slide, I don't know if it's interesting, but let me. Yeah, this is the regressor. T is a parameter, can be chosen. Now we will discuss exactly this T. Is the new thing basically in the regressor. We have a parameter more to be used. Could be an advantage. Could be an advantage. Look, I don't know if it's well visible, probably now better. But just the concept, you don't have to learn this calculation. What I did here is exactly what I told you until now. I calculate y hat x1, considering x1 here, starting from k equal 1 up to n. Here I put it in general up to n. We can see. That's remain the same. I put here b1 because k equal 1, x1, then a1 cosinus 2 pi x1. T is given, as I told you before. We will see if it's not given, we have some problems, but I will discuss later. And then I proceed the same for x. For k equal 2, no? But with x1. This line is calculated by x1, as I told you before with words. Now it's clear what I intend. It's exactly what I did for for the polynomial. But of course, here it's a little bit more, I don't want to say more complicated, but we have to be careful. We have two elements, sine and cosine. The structure of the regress is different. Basically, I'm considering, roughly speaking, yeah, if you look here, no? In this line, we are considering, roughly speaking, different sine and cosine with different frequency. No? This is because k is represent exactly somehow the period or the frequency, if you want. No? I don't know if this is clear. Look at this, for instance. No? This sine of 2 pi and so on. If you write this sine of 2 pi multiply x1 divided t divided 2, yeah, we can see that with respect to I show you that we have in a picture. I show you, we have the different period, no? Of the yeah, basically this is twice faster than this one. I do the same for x2. I don't need to explain. I do the same until xm, and I have this expression here. And then look, this matrix which we have seen in the slide can be reseen here with possible calculation. Assume that t is given. Assume that t is given. Here we have exactly an exploration matrix in which everything is known. If t is not given, if the problem includes, as before, to optimize t, not only n, to optimize t, we have also the problem to optimize with respect to n and respect to t. Before we have just the problem to optimize respect to n, do you remember? Here we have also the problem with respect to t if t is not given. Because we have two parameters to be optimized, n and t, not convex optimization problem. Before simulating, I showed you another slide. It could be that we don't have time to simulate today. I will simulate next week. And so next week we will introduce together. It could be that, no, I don't think so. Let me conclude with theory next week. I will restart with this slide here, and I do the simulations in using trigonometric functions. And then we will start with PSO, very important topic, because this is a solver. I will clarify what is the meaning of a solver. Very often used because for trigonometry, the polynomial mixed. In general, to optimize not convex optimization problems, or to attack. No? Periodical function, we will see next week, can be used nevertheless, even though the function or the data, in this sense, because we are speaking mathematical on a function, but the data appears not periodical. Periodical basically means to mathematically to repeat in an infinite domain. This doesn't make sense for us. We have always a limited number of values, but we can nevertheless use, even though in this limited number of value, we don't see any periodicity. But even though I see in a period or a periodicity, I cannot guarantee, nobody can guarantee that we have a repetition later. I think you know the meaning of this sentence here. F of x equal f of x plus t, in which t is the period, for x larger or equal t. This means we repeat the same pattern. Exactly here, I put two periods, just one sentence, and then we will see next week and a very important problem to work with this kind of regressor. I don't know if you heard about the Shannon theorem. In a sufficient condition, I will tell you a little bit next time, which says that the sample time, basically the distance between the value, which is the data, the measurements, should be less than half of the period of the signal which I have. Now, in our case, we have, I already told you before, many periods here. For instance, if I have a 2, what happens? What happens? If I have a 2 function, at this moment, I presented n function. This means n periods. In order to understand here, we can consider a more, let me say, conservative, considering basically, let me see. I don't see. Because we have a sum, no, of function. Basically, we consider the conservative condition, which we consider the shortest period of the function which we have. Basically, this blue, no? But of course, it's extremely conservative. Extremely conservative. This says, if I guarantee this, we will see with the simulation. If I guarantee this, I can obtain a consequent expression in which I can realize, I can build an approximation. If this is not guaranteed, in this case conservative because I consider the blue line the shortest period, it could happen that the representation present some defects or some really mistakes. This is an important theorem which can be considered when we are working with trigonometric functions. Let me stop here. The reason is we have more than one harmonic. Next week, I will reconsider this aspect here together, and then considering this, we will see extremely easy to build this matrices. Of course, for a given t, we will see for a given t and given n, like here, it seems to be this n or the k, k equal n is the maximal. We consider just 2 functions. We will restart from here. I will simulate this particular situation in which we have some problems. And of course, if we want to minimize also t and n, or one of both, it doesn't matter, it's enough one, we have a non-convex optimization problem. And we will open the chapter of non-convex optimization problems, introducing the PSO, which is in the engineer fields very often used. We will see next week. Thank you for your attention. I am here for questions.